direct product of a finite number of groups. In this module, we are going to see about internal direct product, external direct product, and some of the results related to these two direct products. Particularly, we will be seeing the condition under which the internal direct product will be isomorphic to the external direct product. Let us now see the definition of the direct product of a finite number of groups. Let G1, G2, so on up to Gn be a finite collection of groups. The external direct product is defined by the n-tuple. This is given by the ordered pair G1, G2, so on up to Gn such that Gi belongs to Gi. The product is defined by G1, G2, so on up to Gn. G1 dash, G2 dash, so on up to Gn dash is given by G1, G1 dash, G2, G2 dash, so on up to Gn, Gn dash. Let's see some examples to understand this concept better. First example is, suppose Gi is a set of real numbers for I equal to 1, 2 up to n, and the n-tuple product r cross r, so on up to r, so there are n factors here. It is a Euclidean n space r par n. We are using the usual vector addition here. This is an example of the direct product. Let's go to the theorem. The order of an element in a direct product of a finite number of finite groups is the LCM of the orders of the components of the element. That is, the order of G1, G2, so on up to Gn is equal to the LCM of the individual orders of G1, G2, so on up to Gn. The proof: let the identity of Gi be Ei. Then let S denote the LCM of the orders of G1, G2, so on up to Gn. Let T denote the order of G1, G2, so on up to Gn. Since S is a multiple of each order Gi, this implies that G1, G2, so on up to Gn the whole par S is equal to the ordered pair G1 par S, G2 par S, so on up to Gn par S. And this is clearly E1, E2, so on up to En. So we know that T is less than or equal to S, and therefore G1, G2, so on up to Gn the whole par T is equal to G1 par T, G2 par T, so on up to Gn par T. This is equal to E1, E2, so on up to En. Clearly this shows that T is a common multiple of the order of G1, the order of G2, and so on up to order of Gn. Thus S is less than or equal to T. We have now proved that T is less than or equal to S and S is less than or equal to T. Therefore T is equal to S, which implies that the order of G1, G2, so on up to Gn, the product of all these orders, is the same as the LCM of the orders of G1, G2, so on up to Gn. Hence the theorem is proved. Let's see an example. Consider the group G Z6 times Z10. What is the order of the element 3, 1 in G? The solution is given by the order of 3, 1 is equal to the LCM of order of 3, order of 1. That is 2, 10. The LCM of these two values is 10. Similarly, let's see one more example. What is the largest order of an element of G? Using the theorem that the order of A, B is equal to the LCM of the orders of A, order of B. The order of any element of Z6 divides 6 and the order of any element of Z10 divides 10. It follows that the largest order element of G is 1, 1 and that the order of 1, 1 is equal to the LCM of 1, 1, which is the LCM of 6, 10, and that is equal to 30. Let's see one more example in this. How many elements of order 9 does Z3 addition modulo Z9 have? Let A, B belong to Z3 addition modulo Z9. We have that it has the order 9, then LCM of the order of A, order of B is 9. Since order A can have order 1 or 3, then order of B is equal to 9. There are phi of 9, that is equal to 6 elements of order 9 in Z9. Then A can be any element of Z3. So there are 3 times 6, that is equal to 18 elements of the direct product having the order 9. Let's see one more example. Show that the direct sum of Z2 and Z2 has 7 subgroups of order 2. Each element of order 2 has a unique subgroup of order 2, hence it is enough to count the elements of order 2. Since the order of A, B, C is equal to the LCM of the order of A, order of B, order of C, and the elements of Z2 have order either 1 or 2, then every element of the group has order 2 except for the identity element 0, 0, 0. There are 23 minus 1, 22 elements of order 2. Let's see a theorem now. Let G and H be finite cyclic groups. Then G direct product H is cyclic if and only if the order of G and order of H are relatively prime. Proof. Let order of G is equal to M and order of H is equal to N. Therefore, the order of G direct product of H is equal to M times N. Now, we have to prove that the first half of the theorem, in that we assume that the direct product of G and H is cyclic. Now, to prove that M and N are relatively prime, let us suppose that the GCD of M, N is equal to D and G, H is a generator of the direct product of G and H. Since G, H the whole power Mn by D is equal to G power M the whole power N by T and H power N the whole power M by D, and this is equal to the identity element, therefore we get E, E. We have Mn is equal to order of G, H, which is less than or equal to Mn by D, therefore D is equal to 1. Let G be generated by the set of elements G and H be generated by the set of elements H, and suppose that GCD of M, N is equal to 1. Then the order of G, H is equal to the LCM of M, N, which is equal to Mn. This is equal to the order of the direct product of G and H. Therefore, G, H is a generator of the direct product of G and H. Let's see a theorem now. If a group G is the internal direct product of a finite number of subgroups, namely H1, H2, so on up to Hn, then G is isomorphic to the external direct product of H1, H2, so on up to Hn. The notations are as follows: H1 cross H2 cross so on up to cross Hn. This represents the internal direct product, and we have to show that this is isomorphic to the external direct product, which is denoted by the addition modulo symbol. Therefore, this is the external direct product H1, direct product H2, so on up to Hn. Now, the proof. We have to prove first that the H is different from Hi's commute. If Hi belongs to Hi and Hj belongs to Hj with I not equal to j, then the commutator element Hi, Hj, Hi inverse, Hj inverse belongs to Hj, Hj inverse, which is equal to Hj. Similarly, Hi, Hj, Hi inverse, Hj inverse belongs to Hi times Hi, that is equal to Hi. Therefore, Hi, Hj, Hi inverse, Hj inverse belongs to Hi intersection Hj. We can see that the same element belongs to Hj as well as Hi. But we know that this intersection is equal to the identity element E. This implies that Hi, Hj is equal to Hj, Hi. Now, to prove that every element of G is uniquely of the form H1, H2, so on up to Hn, where Hi belongs to capital Hi. Let G be represented by H1, H2, so on up to Hn, and another element G is equal to H1 dash, H2 dash, so on up to Hn dash. Next, we are going to prove that every element of G is uniquely of the form H1, H2, so on up to Hn, where Hi belongs to Hi. Let us consider that the element G is equal to H1, H2, so on up to Hn. The same element G can be represented as H1 dash, H2 dash, so on up to Hn dash. These are assumptions, and Hi dash both belong to the set Hi, where I is equal to 1, 2, so on up to n. Then clearly the product H1, H2, so on up to Hn is equal to H1 dash, H2 dash, so on up to Hn dash for H1 dash, Hn dash. Then H1, H2, so on up to Hn is equal to H1 dash, H2 dash, so on up to Hn dash. Let us consider that this element be here as it is, and we are taking this element on the right hand side. So we are left with Hn dash, this element, Hn inverse. So this element has gone to the right side. So the remaining elements are brought from the right hand side to the left hand side. So this is Hn dash, Hn inverse, that is equal to H1 dash the whole inverse, H1, H2 dash the whole inverse, H2, so on up to Hn dash, Hn minus 1 dash the whole inverse, Hn minus 1, etc. So these elements alone are on the left hand side. Then we know that Hn dash, Hn inverse belongs to H1, H2, so on up to Hn minus 1 intersection Hn. This is equal to the identity element, so that Hn dash, Hn inverse is equal to E. From this element goes to the right, and therefore Hn dash is equal to Hn. We cancel Hn and Hn dash from the opposite sides of the equation, and by repeating the procedure we get Hn minus 1 is equal to H dash Hn minus 1. Now in this equation, H1, H2, so on up to Hn equal to H1 dash, H2 dash, so on up to Hn dash. We are cancelling Hn and Hn dash because they are equal. They are cancelled from the opposite sides of the equation, and by repeating the procedure n times, so we get Hn minus 1 is equal to H dash n minus 1. Eventually Hi is equal to Hi dash for I equal to 1 to n in this equation. So our claim that G can be expressed uniquely is satisfied. Now let us define a function phi from G to the direct sum of H1, H2, so on up to Hn. G represents the internal direct product. So the elements are of the form H1, H2, so on up to Hn. It is mapped onto the direct sum elements, again represented as H1, H2, so on up to Hn. Here it is the direct product. Clearly phi is a isomorphism, and therefore H1 internal direct product H2, so on up to Hn is isomorphic to the external direct product of H1, H2, so on up to Hn. This statement is not always true. It is only true because H1, H2, so on up to Hn are the subgroups. Now we go on to the next theorem. Every group of order p squared where p is prime is isomorphic to Zp squared or the external direct product of Zp and Zp. The proof: let G be a group of order p squared where p is prime. Now since G is a group of order p squared where p is prime, G has an element of order p squared, then G is isomorphic to Zp squared. Let us apply the Lagrange's theorem, and so we arrive at this result: every non-identity element of G has order p. Now to prove that the subgroup generated by A is normal in G for any element A. Suppose not, proof by contradiction. There is an element B in G such that B A B inverse does not belong to the set generated by A. Then the set generated by A and the set generated by B A B inverse are distinct subgroups of order P. Since the set generated by A intersection the set generated by B A B inverse is a subgroup of both the set generated by A and the set generated by B A B inverse, we can say that the set generated by A intersection the set generated by B A B inverse is equal to the identity set E. Therefore, the left cosets of the set generated by B, A, B inverse are as follows. The set generated by B, A, B inverse, comma, A times the set generated by B, A, B inverse, comma, A squared times the set generated by B, A, B inverse, and so on up to A power P minus 1 times the set generated by B, A, B inverse. Since B inverse must lie in any one of these cosets, we can say that B inverse can be written in the form B inverse for some I and j. Cancelling all the B inverse terms here, we obtain E is equal to A power I times B times A power j, which implies B is equal to, this goes to the left, we are taking AI and AJ to the left hand side. So, that is equal to A power minus I minus j. Clearly, you can see that this is an element generated by A, since it is in the form of A power something. Therefore, B is generated by A, but our assumption is this. So, this is a contradiction. Therefore, every subgroup of the form A, the set generated by A, is normal in G. Let X be any element such that it is not equal to the identity element, and let Y belonging to G be any element such that Y does not belong to the set generated by X. Then by comparing orders and by using the previous theorems, we can arrive at this result: G is equal to the set generated by X times the set generated by Y, and this is isomorphic to ZP direct sum ZP. So, we have proved the result. Next, we shall see a theorem. Let G1, G2 so on up to Gn be groups, and let G be denoted by G1 cross G2 so on up to Gn. This is the direct product. Then we shall prove the following results. Number 1, for each fixed I, Gi is isomorphic to the set 1, 1, 1 so on up to Gi 1, 1, 1 etc. and where Gi belongs to Gi. So, the ith position is fixed by Gi, where Gi belongs to Gi, and the rest of the places are filled by 1. Then this particular Gi is a normal subgroup of G, and G by Gi is isomorphic to G1, G2 so on up to Gi minus 1 times Gi plus 1 cross so on up to Gn. So, we are leaving out the ith element here, because since we have G by Gi here, and therefore, this is isomorphic to this particular set. The next result we will be proving is, if X belongs to Gi and Y belongs to Gj for some I not equal to j, then Xy is equal to Yx. The proof. Let us prove the first result. Since the operation is defined component wise, you can see that the operation here is component wise. It follows that this particular set 1, 1, 1, the Gi and then 1 elsewhere, Gi belongs to Gi, is a subgroup of G. Therefore, Gi has been mapped onto this particular element, and clearly this is an isomorphism of Gi with this subgroup. Identify Gi with this isomorphic copy in G. Now, let us consider phi to be a function from G to G1 cross G2 so on up to Gi minus 1, Gi plus 1 so on up to Gn. Now, the function phi is defined by phi from G1, G2 so on up to Gn is equal to G1, G2 so on up to Gi minus 1, Gi plus 1 and so on up to Gn. Clearly, this map is a homomorphism. Let us check it out. Phi of G1, G2 so on up to Gn times H1, H2 so on up to Hn. So, this is equal to phi of G1, H1, G2, H2 so on up to Gn, Hn. So, we are doing the product of these two terms. This is equal to, since this is the mapping here, G1, G2 so on up to Gn is mapped to G1, G2, Gi minus 1, Gi plus 1 so on up to Gn here. So, the same element is going to be coming here also. According to this mapping, phi of G1, H1, G2, H2 so on up to Gn, Hn is equal to G1, G2 so on up to Gi minus 1, Gi plus 1 so on up to Gn, h1, h2 so on up to hi minus 1, hi plus 1 so on up to hn. That is equal to phi of g1, g2 so on up to gn, phi of h1, h2 so on up to hn. So, we have proved that the phi of xy is equal to phi of x, phi of y. So, the homomorphism property has been satisfied. Now, let us see the next properties. All entries in the position j are arbitrary elements of gj for all j. Therefore, phi is surjective. So, homomorphism property has been satisfied, surjective is done. Now, let us see what happens to kernel phi. Kernel phi is equal to the set of all g1, g2 so on up to gn such that gi is equal to 1, the identity element for all I not equal to j. This is clearly equal to gi. This implies that gi is a normal subgroup of g. By the first isomorphism theorem, g by gi is isomorphic to g1 cross g2 cross so on up to gi minus 1 cross gi plus 1 and so on up to gn. So, the result has been proved. Now, we go on to the second result. If x is equal to 1, 1, 1 so on up to gi so on up to 1 and y is equal to 1 so on up to gj 1, 1, 1 elsewhere. So, the ith position has been fixed by gi and the jth position has been fixed by gj. These are the two elements and the indicated entries appear in the positions I and j respectively and 1 elsewhere. Then xy is equal to the product of these two elements, therefore, it becomes 1, 1, 1 so on. The ith position is replaced by gi and so on and the jth position is replaced by gj and elsewhere it is 1. So, clearly we can see that even if they are interchanged they are going to be the same. So, this is clearly yx. Therefore, xy is equal to yx when I is less than j. Hence, we have proved the second result also. Now, let us define the internal direct product of h and k. G is an internal direct product of h and k if G is equal to h cross k, where h and k are normal subgroups of G and h intersection k is equal to the set E, where E is identity element. There is an example for internal direct product of two groups. Example 1, consider the group Z6 comma plus and the following subgroups h is equal to 0, 2, 4 and k equal to 0, 3. Note that h star k such that h belongs to h and k belongs to k is equal to the set 0, 1, 2, 3, 4 and 5 which is equal to G. So, the first condition is met. Also, the identity element for Z6 is E equal to 0 and h intersection k is equal to singleton 0. So, the second condition is also met. Lastly, Z6 is an abelian group. So, the third condition is met, which implies Z6 comma plus is an internal direct product of subgroups h is equal to 0, 2, 4 and k equal to 0, 3. An important thing to note is that not every group can be written as the internal direct product of two of its proper subgroups. Example 2, if S3 were an internal direct product of its proper subgroups h and k, then one of the subgroups, say h, would have to have order 3. In this case, h is a subgroup of 1, 1, 2, 3, 1, 3, 2. The subgroup k must have order 2, but no matter which subgroup we choose for k, the condition that hk is equal to kh will never be satisfied for h belongs to h and k belongs to k. Now, let us come to the definition of internal direct product of finite number of groups. Let h1, h2 so on up to hn be a finite collection of normal subgroups of G. We say that G is the internal direct product of h1, h2 so on up to hn and we write G is equal to h1 cross h2 so on up to hn if number 1, G is equal to h1 times h2 so on up to hn, that is equal to the set n tuple h1, h2 so on up to hn such that hi belongs to the set hi. The second condition, the n tuple h1, h2 so on up to hi intersection hi plus 1 is equal to singleton E for I is equal to 1, 2, so on up to n minus 1. The next theorem will show you that the external and the internal direct products are isomorphic to each other. In this module, we saw about two direct products, namely the internal direct product and the external direct product. We saw various results related to these two direct products, and most importantly, we found out the condition under which these two direct products, namely the internal direct product and the external direct product, are isomorphic to each other. When they are subgroups of the given group, then the internal direct product and the external direct product are isomorphic to each other. I hope this section was useful to you. Thank you.